Hello and welcome to another episode from Spiral Physics Education. In this episode we're going to be looking at the parts of the 3-pin plug, and that's going to include the earth wire, the neutral wire and the live wire. We're also looking at some incorrectly wired plugs and the role of the fuse and the earth wire. We're also going to be looking at why it is that fuses and switches are always in series with the live wire rather than any other wires. So if we have a look at a 3-pin plug and we take the back off the 3-pin plug, we see 3 pins and the cable coming in at the bottom. And in that cable there are 3 wires. So we've got a blue one, which is called the neutral wire. We've got a stripy green and yellow one, which is called the earth wire. And we've also got a brown one, which is called the live wire. And attached to the live wire is a cylindrical device that's called the fuse. And what we've also have is the cable coming at the bottom, and across that we've got a cable grip which grips the cable. It's important that it grips the cable rather than the wires themselves. So the neutral wire, the blue wire, well, that has the potential of 0 volts, or technically just a little bit above 0. And that can be considered as the return wire for the circuit. And the brown wire, which is the live wire, has a potential of 230 volts, and that technically supplies the electrical energy to the device, and then from the device it returns back to the power source via the neutral wire. And the earth wire, well, that has a potential of 0, and that's attached between the outer metal casing of the device, if it has an outer metal casing, and then it's attached to earth at the other end. So if we then look at a real 3-pin plug, this is what a real well-wired 3-pin plug looks like. So we've got the earth wire attached correctly, the live wire and the neutral wire all correct, and we've also got the cable grip attaching the cable grip. And notice that you can't see any of the actual copper wires in this. The amount of insulation that's been stripped is adequate, and there's no wires that are exposed. So let's have a look at some poorly wired plugs and see if we can identify why they're poorly wired. So if we look at this one carefully, we can see that what we've got here is we have the live wire and the neutral wire. They're incorrectly positioned, so they're the wrong way around. So that would be a potentially dangerous plug to use, potentially hazardous, cause electrocution, possibly a fire as well. And if we look here, then the cable has been stripped too much. So it's a different style of cable grip, but the cable grip is not gripping the cable, it's gripping the 3 wires. So that would be potentially dangerous as well if someone was to yank on the cable. That grip isn't going to protect anything. Let's have a look at another one. So here we've got a plug that's actually attached to something called a video cassette recorder, if you know what those are. So if we look carefully at the plug, we can see that there's an error here. There's no wire attached to the neutral pin. In fact, the neutral wire is attached to the earth wire. That's really dangerous, so I wouldn't use that. And if we look at another example, clearly this one has had some damage done to it because of the way that it's wired. If we have a quick look at it, we can see that we've got way too much of the wire exposed. So the wires are in the correct position, but too much of the insulation has been stripped, and we've got too much of the copper wire being exposed in pretty much all of the wires here. And that's very, very dangerous. That could cause an electrocution, short circuits, even an electrical fire. There's so many different things that could happen. And if we look down here, the cable grip, again, it's not actually gripping the cable. It's the insulation of the cable has been stripped too much, and the cable grip is actually gripping the wires rather than the cable itself. Okay, let's have a look at another one. And with this one, we can see that we've got way too much exposed copper wiring again. And if we look down here, the cable grip isn't going to grip the cable. Once again, that seems to be a common error when people are wiring plugs. And that's a very, very dangerous wired plug again, and shouldn't really be used. And in fact, there isn't even a cable grip attached, so it's really dangerous. Alright, so let's have a look at the fuse. Okay, so fuses, well, domestic fuses that we use anyway, usually come in three sizes, 3, 5 and 13 amps. And these numbers mean that if the current were to go above those values, then what we would say is the fuse blows. So we're going to look at, it's not really a good physics term, but we're going to look at what a blowing fuse actually means. But more interestingly, if we were to look inside a fuse, what we'd find is a wire. And you can see that maybe hopefully clearly on this diagram of a broken fuse, that you can see that there's a wire running through the middle of it. And that's the important part of the fuse. So when the current increases, and this is what we need to write in an exam, the wire heats up, the wire then melts, and when it melts, it breaks, and it breaks the circuit. So that's what we need to say instead of a fuse blows. So when you want to say the fuse is blown, what's actually happened is you've got current flowing through it, it's been large enough to heat it up, to melt the wire, and for the wire to break the circuit. So if we were to compare a 13 amp fuse to a 3 and a 5 amp fuse, if we were looking inside them, it's just that the 13 amp fuse has got a much thicker wire, and therefore it requires a much larger current to heat it up to the point where it's going to melt and break the circuit. So that's the difference between a 13 amp fuse and a 5 amp fuse. It's got a thicker wire. So let's do a little bit of a look into the role of the fuse and the earth wire, because they play a role that's very, very important together. So here we've got a kettle that is going to be attached to a 3-pin plug. So it's got a heating element though, and the heating element inside the plug, inside the kettle, is going to do all of the work. So that's where we want the electrical energy to get delivered to, because we want that to heat up the water. So that's got some resistance, but we've got to try and get the electrical energy to our heating element. So we're going to do that by attaching a live wire and a neutral wire to our 3-pin plug. And we're also going to attach a fuse for safety reasons to our live wire, and it's in series with our live wire. And then finally we're going to make sure that there is an earth wire that's attached from the 3-pin plug to the outer metal casing of our kettle, and our kettle does have an outer metal casing. If it didn't, we wouldn't need a fuse, we wouldn't need an earth wire. So if we were then to look at what's going to happen under normal working conditions, we've got the live wire, and the live wire is going to then deliver our live electricity. That's where the 230 volts potential is coming along. So we can consider a Coulomb coming out of the live wire, flowing through the fuse, flowing through our heating element, and that's where the heating element, that's where the work is done. And all of that Coulomb's energy is delivered to our heating element. So remember that the heating element is going to have resistance, and that resistance will actually cause the current to be lower than if if the heating element had a lower resistance, the current would be higher. So it's important that heating element has got resistance, because that's where we want all the electrical work to be done, and under normal working conditions this is what's happening, everything's safe. So let's say there is a fault, and it's a very specific fault, and the fault in this case is that the live wire is frayed, and it's frayed just here. And what happens is the live wire touches the outer metal casing. So this is the most hazardous fault that could happen to us, because it's the one that could cause us to get electrocuted. So this is why it's really important to consider it. So if this were to happen, what we would find now is that the current flows through the fuse, flows through the live wire, but instead of getting to the element, what happens is it flows through the outer metal casing of the kettle and then along through to earth via the earth wire. And that means that the element is not doing any work. So what's happening into the circuit now is that the circuit has got a low resistance. So the current in the circuit increases. And what's going to happen is that the fuse is the only part of the circuit that's going to do any work. So it begins to heat up because the current has got larger. And it heats up and it melts and it breaks the circuit. So this kettle will not work anymore. And that happens a hell of a lot quicker than what I've just showed you now. It happens almost instantaneously. As soon as it gets up to a point that, if it's a 13 amp fuse, as soon as it goes over 13 amps, that wire heats up and melts and breaks the circuit. So what would happen then if the fuse had been placed in series with a neutral wire? Why is it important that the fuse is in series with the live wire? Well, let's consider this incorrectly wired plug and what will happen to it. So actually, when under normal working conditions, it would be fine. It's not a problem. The kettle would still work, the heating element will still heat up, and the energy will get to the heating element, and you still have piping hot water to have your tea or coffee. Not a problem. However, as soon as this fault occurs, this specific fault where the live wire frays and touches the outer metal casing, that's where it becomes extremely hazardous to place your fuse in series with the wrong wire. So let's have a look at the Coulomb, what the Coulomb is going to do now. So the Coulomb is going to come out of the live wire, flow through the outer metal casing and along back through the earth wire. Notice that the current doesn't flow through the fuse, so therefore the fuse can't heat up, and the fuse can't melt, and the fuse can't break the circuit. So at this precise moment, the kettle doesn't work, but it's live. So when it's live and it doesn't work, if someone were to come along and touch the outer metal casing, our flow of current could actually go through us instead, and then we would get electrocuted. And that's why it's important that the fuse and switches, in fact, are in series with the live wire, because we've got to stop the flow of electrical energy to the device, otherwise this can happen. So I hope you found that lesson on fuses and plugs useful, and don't forget to subscribe to the channel. Hopefully it will help you improve your understanding of physics and get those grades boosted. And subscribe to the channel, like I said, and I'll see you next time on Spiral Physics Education. Goodbye.